Today, I'm going to talk about differential private identity and equivalence testing of discrete distribution. I'm Mariam Aliakiparkur, and this is a joint work with Elias Nicholas and Renee Trevetto. We consider one of the fundamental questions in a statistic. Given two distributions on a very large domain, we want to test if these two distributions are equal or far from being equal to each other. Traditionally, the goal was to find the optimal sample complexity. However, modern challenges makes us to think about other aspects, like protecting the privacy of individuals whose data is used by the tester. So the goal in our paper is to find a tester which is both differentially private and uses the optimal number of samples. As an example for this problem, assume you are given a data set of people's salary and you want to test if men and women are getting paid according to the same distributions. Obviously, salary is a sensitive information that people may not want to share, so we need a private tester. Here, we don't have any assumptions about the data, so we're not assuming it's coming from Gaussian or any other specific distribution. Now let's define the problem formally. Assume we have ID samples from distribution P, and we have access to distribution Q, and we want to test if P is equal to Q. By that I mean that we want to output accept with high probability if P is equal to Q, or reject when P and Q are epsilon far from each other. Given how we have access to distribution Q, we can have different versions of this problem. For example, if Q is uniform, we call this problem testing uniformity. If Q is explicitly given to us, meaning that we know the probability of every single domain element, this is called goodness of fit, or testing identity. If we have only ID samples from distribution Q, this is called closeness, or equivalence testing. Now let's define differential privacy. An algorithm is called private if changing one individual's data point in the dataset does not affect the output of the algorithm drastically. More formally, for a given output O in two datasets X and X prime, that they only differ in one location, the probability of outputting O should not blow up if I change my input from X to X prime. There are a ton of work in the area of non-private testing of distributions, and also differential private testing has been considered before. Here are some examples from these two areas. So for the rest of the talk, I'm going to talk about the general framework in our paper and giving you our results for testing identity and closeness, and at the end I'm going to show you our experimental results. Our general framework is similar to most of the statistical tests. We have a sample set X. We compute a statistic f of x, which is a function of x, and using a standard technique in differential privacy, a plus mechanism, we add noise to the target statistic to make it private. The magnitude of noise that we need to add to our statistic depends on the sensitivity of the statistic f, which is essentially the maximum difference of f when we change the input by a little bit. Obviously, adding the noise hurts the accuracy of the statistic, so we have to make it up by drawing extra samples. So the higher the sensitivity of the statistic is, the larger noise I need to add, so I need more extra samples to essentially recover the accuracy. Sometimes this approach is very inefficient, and we have to come up with more ad hoc approach to solve the problem. Let's move on to our result for testing identity. Goldberg provided a reduction from testing identity to testing uniformity. We can show that the reduction preserves the privacy, so we only need to focus on testing uniformity, which I'm going to explain you in a second. But for testing identity, we get the following sample complexity. The first time is required even in non-private setting, and the rest of the terms are essentially the cost of privacy, which are all in an additive form. So it kind of explains for reasonable regime of Cassie, it's very cheap. So let's focus on testing uniformity. We consider two cases. The first one, epsilon is not too small. There is a tester, non-private tester by Peninsky that uses the number of unique elements to perform the test. Fortunately, the number of unique elements has a very low sensitivity, so we can just add Laplace noise and get a private tester with the following sample complexity. In the second case, we consider arbitrary epsilon. There is a non-private tester based on the number of collisions, which is essentially the number of pairs in the sample set that they have they are the same. For example, here there's one collision between the two tens. It is shown that the uniform distribution has the lowest expected number of collisions, so we can use this as a statistic for uniformity testing. Unfortunately, the sensitivity of the number of collisions is very high, so we can't use the Laplace method. We need to use an auxiliary statistic, max, which is the maximum frequency in the sample set. We also showed that the sensitivity of C can be bounded by the Nmax. So we can only use C when Nmax is not too large. So combining the information from both Nmax and C, we can come up with a tester. Since we haven't used the Laplace mechanism, we need to also directly prove the privacy. After these two steps, we essentially get the following sample complexity for our private tester. Let's move on to the testing closeness. So we use the non-private statistic provided by Chanda Coniculus variant. This statistic is based on the number of occurrences of elements I in two sample sets from P and Q. This statistic has a low sensitivity, so we can add Laplace noise to it and make it private and get the following result. Let's move on to our experimental results. We first consider the problem of testing identity. We estimate the error probability while increasing the number of samples. We compare our own results, which are in green and purple, the two previous works. As you can see, our tester based on the number of unique elements converges to zero. Its error converges to zero very fast. Also, we consider testing closeness. Since there wasn't any prior work, we compare it with the non-private version. Here, we estimate the number of samples while we increase the domain size. As you can see, the number of samples are the same for both private and non-private tester, which means that the cost of privacy is negligible. So here I explained you the differential private testers for the following problem: testing uniformity, testing identity, and testing closeness. For open questions, we can think of other approaches that yield to private testers for many distribution. Thank you.